In this video, I'm going to expand and discuss a little bit more in depth some of the properties of a utility maximization solution. So I'm going to look at a utility function that we looked at once before, and this is an indifference curve map of it down here. The utility function is u equals x to the 1/3 times y to the 2/3. And what we're going to do is we're going to discuss a little bit more in depth what we call the equal bang for the buck rule, or equal marginal utility per dollar spent at equilibrium. So what does that mean? Well, let's write down the equations that we use to maximize someone's utility. And so let's take as an example this utility function, and these are the indifference curves down here. And let's look at, say, a budget constraint that looks like this. Let's suppose somebody has $100 and they get to spend that on X down here on the X-axis and Y up here on the Y-axis. And let's suppose that the price of Y is $5, the price of X is $10. So the budget equation will look like this: 10 times X plus 5 times Y equals $100 if they spend all of their money. And we always assume that they do in these kinds of examples. So let's see, given these two equations, then in order to find where this person would maximize their utility, we have the following two kinds of equations. So equation number one dictates that the slope of an indifference curve equals the slope of the budget line. Now let me just go ahead and graph this budget line here real quickly so that we can see this. Let me see, I'll use a red here. And so to graph this budget line, the easiest way is to say, well, if the price of X is $10, he could afford at most 10X. If he bought 0Y, he could buy 10X. And if he bought 0X, he could afford 20Y, since they're only $5 a piece with $100. So we just want to connect these 2 points here with a straight line, and that will tell us all the combinations that he can afford. All right, let me try that again here. Okay, so that's our budget line. So he can afford any point along this red line, and he wants to maximize his utility, and he gets happier as he consumes more Y and more X. And we might say his bliss point is way up here in the upper right hand corner. That's just the happiest point on this graph. He wants to move that way as far as he can. So the two equations we use to solve this utility maximization problem is that in order to get to the highest indifference curve possible, it's going to be a little bit beyond this indifference curve right here. We want the slope of the budget line to be equal to the slope of the indifference curve. In other words, the marginal rate of substitution has to be equal to the ratio of the prices, because the ratio of the prices tells us the slope. Let's just double check that. The slope of this indifference curve, budget line, slope of the budget line is down 20 over 10 between these 2 points. So minus 2, down 20 over 10. The easiest way to get that slope of the budget line is the ratio of the prices, price of X over the price of Y, price of X over the price of Y. And the slope of the indifference curve we call the marginal rate of substitution, and that marginal rate of substitution can be calculated. Here, let me move this over here. The marginal rate of substitution as a derivative is the marginal utility of X divided by the marginal utility of Y. In other words, the derivative of the utility function with respect to X is the marginal utility of X. It also tells us the additional utility you get for one more unit of X, and divide that by the marginal utility of Y. That tells us the slope at which you're willing to exchange X's for Y's, and we'll look at specific numbers in just a second. So that's the marginal rate of substitution, and we want that to be equal to the slope of the budget line, price of X over the price of Y here. Now let's talk about what this means in a little bit more detail. Let me write this expression out though for marginal utility of X over marginal utility of Y for this case so that we can see what it's going to look like. So the marginal utility of X, if you take the derivative of this function with respect to X, I'll put a link to the previous video in case you need to see that where we derive that. The marginal utility of X is, so I'll write out all this here. Marginal utility of X, just the derivative of this with respect to X is going to be 1/3 X to the minus 2/3 times Y to the 2/3. And similarly, the marginal utility of Y function is the derivative of utility with respect to Y, and that's going to be 2/3 times X to the 1/3 times Y to the minus 1/3. And the ratio of those two functions tells us the slope of an indifference curve at any point. So let me go ahead and simplify that. If we divide one of those functions by the other, we're going to simply get Y over 2X. And again, I'll provide a link to that video so that you can see how we did that in a little more detail if you want. Now, the point of this video is to talk about this equal bang for the buck rule whenever you're at an optimum, and it really comes from this equation here. Let's rearrange this equation right here to get the equal bang for the buck rule. And what it involves is dividing both sides by the price of X. We're just going to be moving this down here and multiplying both sides of the equation by marginal utility of Y, so that moves up there. We're basically exchanging the place of these two with a little bit of algebra. And so what we get is, at the optimum, we're going to end up with the fact that the marginal utility of X divided by the price of X has to be equal to the marginal utility of Y over the price of Y. And this is what we call the equal bang for the buck rule, because what it is telling us is that at the optimum, the additional utility that I got for the last X I purchased divided by its price, which we call that ratio here the marginal utility per dollar of X. Marginal utility per dollar of X. So the marginal utility of X per dollar spent is equal to the marginal utility of Y per dollar spent on Y. This is what we call the bang for the buck. So, for example, if I can buy a unit of X and it gives me, say, 10 additional utils, and I have to spend $2 to get it, then what that tells me is I'm getting 5 utility per dollar spent. So divide means dollar. 5 per dollar. 10 total, $2. You get the idea. If I'm maximizing my utility, then it has to be the case that also for the last unit of Y that I buy, I had to get 5 utils per dollar, whatever I spent on it. So let's look at the actual prices we're talking about here. In order to find a maximum, since the price of X is 10, let's change that here. Since the price of X is $10, and the price of Y is only $5, then if I've maximized my utility, then it has to be the case that for the last y I bought, I got half as much marginal utility for it as for the x. Why? Well, because I spent twice as much for the x, it better be the case that I'm getting twice the marginal utility for that x that I spent. So that number has to be twice that number, the marginal utility for y. Now we're going to find the solution and we're going to verify that, and then we're going to look at a couple of counter examples here. Now, I'm just going to assume that you've watched other videos and you know how to find the maximum here, and I'm just going to tell you what this solution is going to be. But basically, the two equations that you're going to have to solve are this marginal rate of substitution, which is y over 2x, equals the ratio of the prices. So y over 2x. So here's the two formulas. I'll just write them over here. Y over 2x equals the ratio of the prices, 10 over 5, price of x over the price of y. That's what I think about as equation number 1. And here's equation number 2, the budget line. Solve those two equations for two unknowns. And what you're going to get is this point right around in here, which is happens to be x equals 3.33 and y equals 13.33. 13 and a third is the optimal solution there. Now let's look a little bit more closely at that solution, and let's make sure, first of all, that it meets this equal bang for the buck criteria. And then we're going to see what happens if we weren't maximizing utility. This is a very common kind of problem that we ask you to do in intermediate micro to make sure you understand this. So let's look at that one point. Let's look at the marginal utility of x and the marginal utility of y, and let's verify that these numbers are the way they should be. Now they have to be mathematically, but let's just see what these numbers look like. Now the marginal utility of x we can calculate by plugging in the x and y amounts into this marginal utility of x formula here. Pause the video, take a minute and do that, and then the same thing for the marginal utility of y. Let's calculate those two numbers by plugging in x equals 3.33 and y equals 13.33. Okay, when I do this, what I got was that the marginal utility of x was about 0.84, which means that at this point, as you're consuming more x, you are increasing your utility at the rate of about 0.84 per unit. And the price is $10, so the marginal utility per dollar is going to be 0.084 per dollar spent. And that has to be equal to the marginal utility per dollar, the bang for the buck. How much extra happiness per buck spent do you get? That has to be equal to the bang for the buck for the y. And so the marginal utility of y I got was about 0.4198. In other words, about 0.42. And when you divide that by 5, sure enough, you get 0.084, which is the marginal utility per dollar spent for the last unit of y. So right there, this is just another way of writing this optimality condition. When you write it this way, it says that the slope of the slope of the indifference curve has to equal the slope of the budget line. The economic interpretation of that is that as you spend your money, you want to maximize your utility. You want to make sure you're getting the biggest value for your dollar. And if you keep doing that, then when you've spent all your money, the additional value per dollar you're getting for the last pennies spent on each good should be roughly equal. So for the last little bit of X, we're getting 0.084 utils per dollar. For the last little bit of Y, we're getting 0.084 per dollar as well. Now let's look at this a little bit different way that might make more sense to you. This is the way it makes more sense to me. Let's look at a case where we're obviously not maximizing our utility. So what if we were on the budget line, this red line, but we were consuming, oh, let's say somewhere around here, around this yellow point. And I'm making a big yellow point so that I can fudge the numbers and make them into whole numbers here so that we can think about it. So let's suppose instead we weren't maximizing our utility. We're on a much lower indifference curve here. Let's look and see what's going on. Let's suppose that we were buying about 7 X's and about 5 Y's. And we might not quite be able to afford exactly that amount with our budget, but let's just assume we can. It's going to be close. Then let's calculate for 5 Y's and 7 X's the marginal utility of, let's calculate 3 things. First, what is the marginal utility of X at that point? So let's calculate those 3 things. What is the marginal utility of X? 2, what is the marginal utility of Y? And then 3, let's calculate, let me write 3 over here. 3, let's calculate the marginal rate of substitution and then of X for Y, and then let's interpret that. So again, pause the video, plug in the numbers 7 and 5 into the marginal utility of X, marginal utility of Y, then divide them, or just use this simplified version. Either way will give you the same answer, and get the marginal rate of substitution and think about what that means. Okay, when I plug those numbers in, for a marginal utility of X, I get a number that's around 0.25. It's actually a little bigger. It's 0.266. But let me, for the sake of having easy numbers to talk about, let's say that's about 0.25. It's a little off. It's a little off. And the reason I'm rounding it that way is because the marginal utility of Y is close to 0.75. Now, when I'm doing calculations, I would never fudge the numbers like this. But for discussion purposes, this will make it a little bit easier to talk about. Now, what's the marginal rate of substitution of X for Y? If we just plug in Y equals Y equals 5 and 2X equals 14, we're going to get 5 over 14. And I'm going to say that's close to a third. So that's why I'm fudging the numbers so that we can easily talk about it. 0.25 over 0.75, it's around a third. Not exactly. And I would never fudge calculations like this except for discussion purposes. That makes it easier. What does that marginal rate of substitution mean, that 1/3? Well, what it means, roughly speaking, is that if you want to keep me just as happy, if you want to keep me indifferent, then what you could do is you could take one Y, you could give me one more Y. So let's do that. Go up 1 Y from 5 to 6. But to keep me happy, just as happy, when you give me one more Y, well, I'm getting that backwards. I'm getting that backwards. Let me erase that point right there. Let's move downwards to keep it. We'll do it both ways. If you give me one more Y to keep me just as happy, you could take at the rate of about 3 X's. So 1, 2, 3. And that's going to roughly keep me on the same indifference curve. Now you see that I only moved over 2 X's here. And the reason is because that slope is getting steeper as we move. But a line tangent at that point is going to have a slope of 1/3. But what that tells us is basically at that point for small movements, give me 1 Y, you can take 3 X's. Now moving in the other direction, let's interpret it that way. Moving in the other direction, you could take 1 Y from me, and in exchange, give me 1, 2, 3 more X's. and that will get me back on the same indifference curve. And here we actually can move over 3 because the slope is changing less rapidly in this direction. It's getting steeper a lot more quickly over here. So that 1/3 means take 1y, give me 3 x's. Or take 1/3 of a y, give me 1x, is an easy way to interpret that marginal rate of substitution. Now, if we're not maximizing, so that marginal rate of substitution tells us I'm willing to trade 1/3 of a y for 1x, 1/3 of a y for 1x, or 1y for 3x. That's what I'm willing to trade. Or I'm willing to, if you give me 1y, I'll give up 3x's. That's not an optimum because at this point, you don't have to give up 3x's to get 1y to stay just as happy. Every time you give up 1x, let's look at the budget line. What do you have to do? Well, if I give up 1x, it's $10. How many y's can I get? 2. I can get 2 y's when I give up 1x. So if you gave me 1y, I'd be willing to give up 3 x's, but we don't have to do that with the prices the way they are. So to make this a little more concrete, as I give up 1x, it would make me just as happy to get 1/3 more y. Give up an x, give me 1/3 more y. Now this is getting steeper as we move, but basically that's the idea. Give up 1x, give me 1/3 more y, you keep me just as happy. But as I give up 1x, I can buy 2 more y. 1, 2. Well, that's got to make me a lot happier then, doesn't it? And same thing here. If I give up another x, I'd be just as happy to get about 1/3 or 1/2 of a y. But when I give up another x, I can get 2 more y's. Well, this is increasing my utility then. So what we're trying to do is compare, what are you willing to do? That's the marginal rate of substitution. What are you willing to do that would keep you the same happy, with the same happiness, compared to what could you do when you give up 1x? You could get 2y. Well, if you can get more x than would keep you just as happy, you must be able to get happier moving in that direction. So let me summarize and give you a couple of tips for when you're asked to do problems about this equal bang for the buck rule. If you're maximizing your utility, then the marginal utility of x per dollar divided by the price, the word per means divide, so marginal utility per dollar has to be equal marginal utility of y per dollar. At a point that's not an equilibrium, like this yellow and blue point here, the marginal utility per dollar of x is going to be, well, let's actually calculate it. We know the marginal utility of x is 0.25 divided by the price of x is $10. All right, so that equals 0.025. Let's compare that. Let's put a question mark because it's not going to be equal, or let's just say not equal. The marginal utility of y we calculated at that point was 0.75 divided by the price of y. Let's calculate the bang for the buck there. Well, 0.75 over 0.5 is going to be, oh sorry, not 0.5. That should be $5. 0.75 over $5 is going to be 0.15. What does that tell us when we compare those two numbers? Well, since at that point you're getting a lot more value for dollars spent on y than for dollars spent on x, this tells us what you're doing wrong. You want to move in the direction where you're buying more y and less x. In other words, you want to move in that direction. Less x and more y is going to get you to a higher indifference curve. So anytime you see a problem where the marginal utility of $ for y is higher than the marginal utility for x, spend more money on the thing that you're getting higher bang for the buck, and less on the thing with lower bang for the buck. And eventually, when they become equal, you'll be at your maximum. So hopefully this has given you some insight, a lot of numbers, a lot of calculations going on there, I know, but some insight into where this equal bang for the buck rule comes from and how you can make sense of interpreting those kinds of questions. As always, if you have any questions, leave me a comment or question in the comment section below, and good luck on your intermediate micro studies.